talk about the step that you should have to design the FIR digital filter. Okay, so basically we have few steps, okay, but you don't have to remember everything. Why? Because of if you really understand the reason why we need to have filter design just now, because of for us to solve two problems, one for infinite time, another one is about non-causal. I think you don't have to remember each and every step. Okay, so but here I'm going to summarize what you should have for filter design. Alright, so first step, what you should have in filter design is actually what is your omega p and what is your omega s value. So basically, how to get your omega p and omega s, it is based on the equation of you have 2 pi fp over ft, and then for omega s you have 2 pi fs over ft. Okay, maybe some of you may wonder how to get the value of your ft. Okay, so ft is actually your sampling frequency. Okay, so ft equal to 1 over sampling period. Okay, this is your first step. Okay, for second step, you need to determine your Windows type. Okay, so how to know your Windows type? It is actually based on the value of the minimum stop band attenuation. Right, if let's say you cannot find your minimum stop band attenuation value in the question, you can find that based on this formula. Okay, alpha s is actually we have alpha s, which is referring to stop band attenuation, equal to minus 20 log delta s. Okay, why you have to refer to delta s value? Because if you still remember, for our delta s value, it is actually the value is very low, which is approaching to 0. That is why we have to pick the delta s value. Okay, maybe some of you may wonder also why what happened if we have two delta s value. Okay, so if you have two delta s value, then you have to pick the very minimum value. Why? Because of very minimum value will give you a very minimum stop band attenuation value. Okay, alright, so next, okay, you need to determine what is your transition band value. Okay, so again, transition band value you can easily get from your tolerance diagram. So delta omega is actually, it is either omega s minus omega p if the signal is if the filter is low pass filter, and it is omega p minus omega s if the signal is, if the filter is high pass filter. Okay, so depend on your what type of filter you have to design. Okay, next you have to find what is capital M value. So for you to determine capital M value, you have to refer to table number 5 in the given formula sheet. Okay, so basically in table number 5, you can see you have the window type, you have the minimum stop band attenuation value column, and then you have transition band column, and you have the function for the window itself. Okay, so for you to determine M, you need to refer to transition band column. transition bandwidth. If I'm not mistaken, in table number 5, it said about transition bandwidth column. Okay, so for you to, if you refer to that table, you may wonder, okay, which transition band you need to refer. Okay, in step number 2, you already determine what type of window, okay, you are going to use. Okay, so basically based on the window type, okay, you refer to that row. Okay, let's say based on the minimum stop band attenuation value, you know that you have to use window, for example, Hamming window. So you have to refer to Hamming window rows, and then you select the transition band value based on the Hamming window. Okay. You need to know what is your cutoff frequency value. Okay, so again, step number 3, step number 5, these two values you can easily get from the tolerance diagram. Okay, so omega C is actually the value in between. So basically, if you look at the formula, it is actually the average between two values. Okay, the average between omega S and omega P. Okay, you need to determine your filter coefficient. So when we talk about filter coefficient, you need to determine your Hn. So how to get your Hn? Hn is equal to H desired N times your window function. Alright, so basically again, H desired N, you need to refer to table number 6. Window and function you can get from table number 5. Okay, so basically in table number 6, okay, you can see we have 4 types of filter: low pass, band stop, high pass. So maybe some of you may wonder, oh, how to know our filter is according to that types. Okay, again, refer to your specification, or you can refer to your tolerance diagram. If you still remember, for the first step, you have to sketch your tolerance diagram. So based on the tolerance diagram, you may know what type of filter you need to design. Okay, so refer to that. Okay, alright, after you know what type of filter you need to design, next, okay, you need to refer to table number 6. Okay, in table number 6, if you look at, for each filter, we have 2 N values. One HDN value is for when N not equal to 0. Another column is when N equal to 0. So what happened? Make sure during exam, you have to include the equations. Okay, let's say we have, you need to design low pass filter. Then you refer to low pass filter row in table number 6. Okay, next what you have to do is you need to jot down the equation for HDN when N equal to 0, and another equation for N not equal to 0. Okay, that is for HDN. Okay, and then we have WN. Okay, your window function. Okay, this window function you need to refer to table number 5. Okay, so if you look at table number 5, refer to the last column. Okay, so again, for window type, we have several windows. Okay, so again, refer to step number 2. You have your window type. So let's say if your window type is Hamming window, then you refer to the last column of Hamming window. Okay, so you just copy your Windows function. Okay, next what you have to do is you have to make a table. Okay, your table should consist your N, HDN values. We have your WN values. and what is the value of your Hn. Okay, why you need to have a table? Okay, this one to make your life easy lah when you want to do the calculation. Okay, again, for the n value, this part you need to refer to the question. Okay, this part you need to refer to the question. If, okay, the objective of step number 6 is all about you have to determine the filter coefficient. So basically, this is your filter coefficient, Hn. Alright, so for you to determine Hn, you need to know your coefficient. When we talk about coefficient, it is all about n. Okay, so what happened? Let's say in the question is already stated that you have to find the coefficient for n equal to 64, 65, 66. Let's say. So you have to find the value for 64, 65 and 66. Okay, and if let's say the question didn't state what is your coefficient value, I mean your n value, then you have to use by default value. So in by default value, you can just use 0, 1 and 2. So what you have to do next is you just substitute when n equal to 0, substitute inside this equation. And then for when n equal to 0, you substitute to this equation. Okay, when n equal to 1 and 2, you have to use this equation. Why? HDN when n not equal to 0. When n not equal to 0, you have to use this formula, this equation. Okay, so for 1 and 2, you have to refer to this equation. For Wn, you just have one equation, so you have to substitute the value when n equal to 1 and 2 using this formula. Okay, bear in mind, these three equation is actually in radian. So please make sure that your your calculator mode must be in radian. Okay, I repeat again, make sure when you do the filter design, when it comes to determine the filter coefficient, make sure your calculator mode is in radian mode. Okay, after you get all those values, then you need to conclude. Okay, so basically remember again, for filter design we have two problems. One because of infinite time, another one because of non-causal issue. So for you to solve infinite problem, you need to do windowing. So basically step number 2, 3, 4 is all about windowing. Okay, alright, so step number 7, it is all about to solve the non-causal issue. So you have to make a line of a conclusion. So you just put to make a signal causal, the signal is shifted to the right by M point. Okay, why to the right? Because, okay, remember the definition of causality, the signal must be at the right sided signal, right? So that's why the signal is causal. M point you can get from here. Okay, so based on step number 4, you can get your M point. So again, I want to repeat, why M? Why not capital N? Okay, again, remember this. Okay, we do the windowing and then we need to shift at this part, the signal at the left sided. If you look at this signal, this is two-sided signal, which is referring to non-causal signal. So we want to shift this signal, the left-sided signal. So because of this one, we need to shift by M. Why by M? Because of, if you look at this range, it is from minus M to 0. So basically, it is N point. Alright, so because of that also, here you have to write to make a signal causal, the signal is shifted to the right by endpoint. Okay.